Welcome everyone to chapter 3. Now we're going to be looking at acids and bases. And so when we look at acids and bases, what we're really looking at is the movement of a proton or an H+, and we'll definitely talk about that quite a bit. This is a specific type of reaction that you may have looked at a bit in Chem 1 already, but what's really key to these reactions is not only that they come up all the time, but that there is a certain relationship between the acids and bases that we really need to understand well if we're going to understand how acid-base chemistry works. Furthermore, many acids and bases don't just exist as this straightforward point A to point B idea that we've looked at a lot in chemistry, but we also saw for equilibrium reactions doesn't quite apply. Most acids and bases will exist in some state of equilibrium, and so understanding that and how to apply what you've learned in equilibrium will be very important here for acids and bases as well. This is kind of two parts of our acid-base series. This is an introduction to acids and bases, and in the next video we'll be talking about buffers, which are a more sophisticated type of solution that resist pH changes, very important biologically, and certainly part of your General Chemistry 2 course as well. And with that, we'll get into the video and learn a bit more about acids and bases. So the first thing we want to look at here in acid-base reactions is what exactly do we mean by an acid and a base, as this will greatly help us recognize an acid-base reaction and understand what is going on when we have some sort of acid-base chemistry that's present. And as we look at our definitions, we're going to start with this Bronsted-Lowry definition, which focuses on protons, or H+. And as we look at H+, we want to recognize that this is indeed a proton because hydrogen has a single proton, no neutrons generally speaking, and an electron. So if we turn this into H+, what we've done is remove that electron, and literally all we're left with is a proton. So H+ proton, this is going to be interchangeable. And when we look at an acid, this is a proton donor. It's going to be losing an H+. And as we look at a base is a proton acceptor. It's going to be accepting or gaining an H+ from another substance. And when we have an acid-base reaction, we basically have one species that acts as an acid that's going to donate this proton, and another species that acts as a base that's going to accept this proton. For example, the one shown here, where we have HCl and water, H2O, that are going to combine, and we see that HCl is the acid because it's losing a proton, right? It's going from HCl to Cl-. That's the species on the right side of this equation that represents what is left over after this proton has moved around. In this case, it's moved off of HCl. That's our acid. Water's the base. The proton has moved to the water and has become H3O+. What's left of water after the acid-base reaction is water with an extra proton, an extra H+, and that's going to be H3O+ here. And so we see that we have one species that's an acid, one species that's the base, and this proton is effectively moving from the acid to the base. In other words, the acid is donating the proton, and the base is accepting a proton. And just to drive this point home one more time, H+ is a proton, and we're going to just say proton more often than we say H+. It just rolls off the tongue a little bit better, and it's just what chemists are going to refer to and what your text is going to refer to. And you really just want to be very clear that if we say a proton and we want to represent this chemically, this is what we're representing. It's H+. Okay, so now is a good opportunity to see, well, can you recognize what's acting as an acid or a base in a reaction? So go ahead and pause the video here and go ahead and give this one a try, see if you can get the right answer. We're looking for which one is acting as a Bronsted-Lowry acid here. All right, so hopefully you've gotten to pause the video and decide on an answer. And the answer here is going to be H2SO4, right? What is acting as a Bronsted-Lowry acid? It is this H2SO4, sulfuric acid, because as we look at this reaction, we see that F- is becoming HF, and H2SO4 is becoming HSO4-. Which one is donating that proton, losing the proton? It's going to be the H2SO4, right? Sulfuric acid donates the H+ to the F-. Therefore, it will be the acid. The fluoride F- ion will be the base. All right, let's try this one more time. If we have the following reaction, what's acting as our Bronsted-Lowry base? Go ahead and pause here again and see what you think. All right, so hopefully you've been able to get the hang of this a little bit. We really want to look at the reactants becoming some very similar looking product that differs by a proton, and that for both of our acid and base reactants, right? And in this case, the one that's going to accept the proton, gain the proton, is the OCl minus. And this one is going to become HOCl by gaining the proton. H2O is going to become OH minus by losing the proton. Water's the acid. OCl minus is the base. One thing you might notice here, right, is that water we've actually seen act as an acid and a base, and we're going to take a look at that later. The relativity of an acid and a base in a reaction is what's going to determine its role in a chemical reaction. And I think one of the challenging things about the acid-base chapter, we can't just say a chemical species and say, oh, well, this is always an acid. Because whether it's going to donate its proton or not, or even accept a proton potentially versus donate a proton, is going to depend on how much the other chemicals in the species do or do not want to hold that proton. So it is this kind of relative chemistry where we're looking at where that proton would rather be in defining what's going to be the acid or the base. Okay, one thing we want to look at as well is that bases are often negatively charged anions. And a big question is, well, how do we even get them into solution in the first place? And here we want to recall our solubility. Ionic compounds are going to provide these basic anions. And so if we want to look at carbonate, for example, and we want to bring carbonate into solution, we can't just take CO3 2- carbonate and drop it into solution. We need to have it as part of an ionic compound because we don't just have stuff with -2 charge sitting around on the shelf, practically, right? It's going to exist as an ionic compound. But if we have this sodium carbonate, we recall that sodium-containing compounds are always very soluble, so this Na plus is not going to affect any other side reactions that could potentially be in the solution. And effectively, if we take Na2CO3, it's going to give us carbonate. Once we have that in solution, carbonate with water will engage in the following reaction, right? Where we have CO3 2- that's going to accept a proton from the water, therefore acting as a base, and the water acting as an acid. And this sort of two-step reaction is one that is very important to understand as you're studying acids and bases. Because very often we are going to just want this negatively charged anion, but in problems you might see, well, what if I add sodium carbonate, right, Na2CO3? And if you're not being acutely aware of this multi-step, the dissolution and then the equilibrium that this base and acid undergoes, it can be very confusing what the sodium is actually there for. But it's there because we cannot just have isolated carbonate, and therefore when we want to put an anion into solution, we're almost always going to bring it there with an alkali metal. So whether it's sodium or potassium, those are by far the two most common. That is what we're looking for, right? Sodium carbonate is effectively bringing carbonate. The sodium is inert. If it was potassium carbonate would be inert as well. If we have 1 mole of sodium carbonate, we're going to get 1 mole of carbonate, right? Because in 1 mole of Na2CO3, there's 1 mole of CO3 2-, 1 carbonate. Okay, as we're looking at these, perhaps you've noticed that when we go through the reaction, like OCl minus to HOCl in this case, well, we're gaining a proton, right? But what if we look at it in reverse, right? If we look at this in reverse, what's the acid and what's the base? And if we look at this in reverse, we would see that, well, if we go from OCl minus to HOCl, this is the forward direction, that's acting as a base, right? It's accepting a proton. But if we look at it in the reverse direction, we would see the following, right? That HOCl is becoming OCl minus. And in reality, there's this kind of equilibrium relationship, right? That it doesn't just go forward, it also kind of goes in reverse. And so what we're going to define is that we have our base, let's say our base is OCl minus, and it becomes HOCl, that's going to be called the conjugate acid of OCl minus, because if it is to lose a proton, it becomes the base. If the base is to gain a proton, it becomes the acid. And so we have this acid-base conjugate relationship that exists, where they differ by a proton. And the same is true for the water, right? Water is acting as an acid to become hydroxide, OH minus, but if that hydroxide is to gain a proton, it will be acting as a base and it'll become water, the acid. So this acid-base conjugate relationship is very important because as acid-base chemistry occurs, you're going to form the conjugate. And if the conjugate does its acid-base thing, you're going to form your original species once more. So differing by a proton gives us this conjugate relationship, and it's very important to recognize these things. We can see this in the following diagram, where if we look at a reaction, so let's say this reaction below, where we have acid and base coming together to form the conjugate base. This is OH minus, as water will be acting as an acid here. And our conjugate acid, this is NH4 plus, as the base, NH3 ammonia, is gaining a proton. We have our reaction, right? And on the one hand, we have water that's losing a proton to become OH minus. On the other hand, we have NH3 that's gaining a proton to become NH4 plus. And so there are two conjugate acid-base pairs here, right? The acid with the conjugate base, the base with the conjugate acid, that are being demonstrated in this acid-base equilibrium reaction. Okay, so go ahead and pause the video here. Think about what is the conjugate base and conjugate acid of the following things. And remember that acids are proton donors, bases are proton acceptors, and the conjugate is going to differ by a proton. So go ahead and pause the video, try to write these down, and see if you can come up with the correct solution. All right, hopefully you've had a bit of time to write these down. The conjugate bases here are going to be ones that have lost a proton compared to the acid, because when they act as a base, they're going to gain a proton and regenerate the acid. So here are our answers, right? H2CO3 loses a proton, it becomes HCO3 minus. It's lost one hydrogen and a positive charge to leave it with a negative charge. And the following is true for the HPO4 2 minus and our water. For our bases, we want our conjugate acids. These are ones that are going to gain a proton to form the conjugate acid. And if we have our conjugate acid and it loses a proton, it'll form the base. And so here are the solutions there. One thing we notice is that water can behave as an acid or as a base, right? We have the conjugate base of water, which is OH minus. This is what happens if water acts as an acid and loses a proton. And we have the conjugate acid of water if it acts as a base, H3O plus. This is what's left over as it gains a proton. And so, again, water can act as either, and what it's going to do is going to depend on the other species in the solution. If there's something that really wants to act as an acid and give up its proton, water is going to act as a base, right? It's going to pick up that proton because it doesn't mind as much grabbing an extra proton. And if we want to put water with something that really wants to take another proton, really wants to act as a base, then water can act as an acid and become OH minus. So what water ends up doing will depend on the other species, and it's definitely not the only one of these species that will do such a thing, so are very important to be aware of. On this list, right, we actually have several of these. The bicarbonate conjugate base here can lose another proton. We've actually seen that earlier in this chapter. And we have NH3 as one of the conjugate acids, ammonia, which we showed how it acts as a base in the previous slide as well. So many of these species exist. We call them amphoteric or amphiprotic species, meaning they can exist as acids or as bases. Okay, again, amphoteric substances. The most common is water, but another is the bicarbonate ion. And so here we have bicarbonate that's existing again with OH minus. This is something that really wants to pick up a proton more than bicarbonate wants to keep it, and therefore it will act as an acid. But if we put it with something that really wants to donate a proton, like H3O plus, then it will accept that proton from H3O plus and act as a base. So in the first situation, we have it acting as an acid, creating its conjugate base. And in the second, we have it acting as a base, creating its conjugate acid. And so this is a very important theme. Like I mentioned, many things exist as amphoteric or amphiprotic substances, and what they do is going to depend on the other species in the solution. Last thing we want to discuss is that there are strong and weak acids and bases. And when we refer to this, what we're not referring to is the amount of acidic or basic activity. What we're really talking about is the extent of ionization, meaning whether or not we're in an equilibrium reaction. So if we have a strong acid, it can ionize completely. And this is like hydrochloric acid. HCl plus H2O goes to H3O plus and Cl minus. If we have 1 mole of HCl, it's going to give us 1 mole of H3O plus and 1 mole of Cl minus. In contrast, weak acids and bases ionize only to a small extent, and we have an equilibrium reaction. And so here we have acetic acid in the presence of water will make some H3O plus and some acetate ion. And here, if we want to know the extent to the reaction, we're going to need to know more about the equilibrium, which means a K expression. And that's going to be a big part of understanding acids and bases. As I mentioned, this is not the amount of acidic activity. we can have a very dilute strong acid solution, and maybe you've worked with that in the lab where you may have 0.0001 molar HCl. There's just not that many HCl molecules in that solution, and therefore, even though they all turn into acidic activity, it's just not that much in the solution, and it's not a very strong isn't the right word, it's not a very acidic activity solution. The solution doesn't have a ton of acidic activity. In contrast, we could have really, really high concentration solutions of weak acids that, even though they don't create all of them into effective acid, we still can have a very solution that's a very acidic activity, a solution with a lot of acidic activity. So definitely keep those two things in mind, right? That even though we're saying strong acid or a weak acid, that doesn't mean that strong acids are going to be more corrosive than weak acids. All right, so that is our acid and base video introduction. Next video, we're going to be talking about buffers, so a special type of solution that can help to regulate its pH, very important in biological applications and whatnot. And I look forward to discussing it with you then.